Good afternoon, everyone. Welcome to our presentation on cable-driven reconfigurable robots based on tensegrity structures. I'm gonna talk about background, structure design, robot control, and how we do experiment. A robot for exploration and reconnaissance in offshore areas is targeted. It should meet the requirements of high-altitude launching, automatic switching, low energy consumption, and small size and easy hailing. We plan to design our robot from a bionic perspective. After literature review, we finally chose the near-it as the biomimetic object. It is small, flexible, and can move well in the shallows. Considering the structural features of the near-it, we choose the spherical tensegrity structure as the basic unit. Each one has 6 rods and 24 strings. It has high stiffness to mass ratio and high cushioning capacity. In order to reduce the number of motors and make the robot with smaller size, we use wire instead of rod to drive the robot and design gear sets to steer. The robot is composed of spherical tensegrity models on two sides, one knuckle model in the middle, and connecting boxes between the models. The connecting box can connect more units to make the whole robot look more like a near-it. The strings are divided into springs and ropes. They imitate warm circular and longitudinal muscles, respectively. To control the deformations, there are two ways of rope winding: axial and circumferential compression. These two methods simulate the compressions of longitudinal and annular muscles of the near-it. The knuckle model is for steering, including a gear train and a spherical tensegrity. The gear train converts one occultation to several degree of freedom rotations. It is more energy efficiency. Spherical tensegrity provides peristaltic expansion and supports the whole body of the robot. Because the body of near-it can be divided into many sections, we use the connecting boxes for automatic stitching. It can realize magnetic positioning and automatic clamping. To sum up, the robot moves forward by changing the friction force of each part to the ground. Having noticed the near-it alternative is varicose feet on the ground, we design a crank-shaper mechanism mounted on each bar. It sticks out when the tensegrity module compresses and takes back when recovery. After that, we designed the robot control board using OpenMV and laser sensors for perception. Then, we developed the software to receiving sensing data. Each part is tested separately, and they all work well. Here's a video of the robot moving on the flat ground and sand. The robot can also roll on the grass. In addition, the tensegrity structures makes it has good buffering property. According to our rope winding method, a single tensegrity model has good motion characteristics. In conclusion, the robot can adapt to a variety of environments and terrain. It is modular and reconfigurable. It has less actuators, small size, with low energy consumption, and has a long battery life. That's all my presentation. Thank you all for your patience.